Hello. Today we'll be talking about paged attention. So, paged attention is one of the optimization strategies that VLLM uses for serving models in the inference mode. And there are some interesting things that make paged attention so fast at serving inference at scale. So, before talking about paged attention, we need to understand what were the problems that existed before paged attention was introduced. So let us take a look at how a KV cache was actually managed before paged attention was introduced. So initially, whenever you want to create a KV cache for an input sequence, what you used to do is to allocate a fixed size memory block, which is contiguous. So inside of that block, we'll have multiple contiguous memory locations. And as soon as you get tokens autoregressively one by one, you start occupying these individual memory locations one by one. So anytime you want to read the KV cache, all you have to do is start from the beginning of the block, and then you access all the elements in the sequence, just like you access any array. So there are two paths for this mode of operation. One is the happy path, where you have enough space available in the block that you have currently allocated. So anytime a new token comes in, you have room for it to be placed. Okay. And that is where everything works perfectly fine. But things get a little bit tricky when the block that you memory block that you have allocated does not have enough space for the KV cache to grow for that particular sequence. So what to do then? Since the requirement is very clear, you want to be able to access all the tokens in a sequence, you need a contiguous block. But the current block is not big enough. So what happens is that you will have to allocate a bigger buffer where there is enough room for the KV cache to grow, right? So that is the second case, which is the not so happy path, where if the memory buffer gets full, you copy everything to a new bigger buffer and you release the previous memory. And whatever new tokens come in, you start placing them as usual. And now you have a bigger block of memory for the same KV cache. So this is how traditionally we can say KV cache was managed in the memory. Now, what is the problem with this kind of setup? So there are two interesting problems that we have. One is called the internal fragmentation, and the other is called the external fragmentation. So there are two ways that you can partition your memory. One is using fixed sized pages, and the other is using variable size blocks. So when you start creating fixed size pages, so let's say you allocate a memory buffer that is suitable for storing, let's say, 100 tokens. Okay, but you end up using only maybe 80 spaces out of it. So the remaining 20 spaces in the fixed sized buffer will be wasted, and it cannot be used for any other sequence in the KV cache, right? So this particular page or this particular block of memory, contiguous memory, is no longer useful for another sequence, right? And that is called an internal fragmentation. Why is it internal? Because the memory is vested inside the fixed size memory block. The other type of problem that we can run into is the external fragmentation. So what happens during external fragmentation is that when you have variable size of uh, memory blocks, so it is natural to have some blocks that are smaller, some blocks that are larger. Some blocks maybe they started out as small, but then as the memory requirement grew, you had to copy them to a different location. And now the requirements in this new memory space are much larger, so this block grows in size. So, due to this, there is a possibility that whenever the scheduler is looking for a memory location of, let's say, 10 MB, it is unable to find this location of 10 MB. Maybe there is another location that is, let's say, 8 MB or 9 MB, but not a 10 MB, right? So the requirement that I have is much larger than the internal memory space that I have. So that is when the external fragmentation occurs. Interesting part about the external fragmentation is that even if the overall free space that you see in your system is much larger than the memory that you actually require, you may still not be able to allocate it for your resources. The reason being that you don't have a contiguous block of memory that you need. Instead, you have chunks of memory that is scattered around in the entire disk, right? So this is another problem that you face with the traditional KV cache. Now, let me walk you through the actual CUDA memory hierarchy before we even understand the scale at which it is difficult to manage the memory for your paged attention. So in CUDA, we have two major types of memories. One is the global memory, which is very huge in size. It's like in GBs. And then there is the SRAM, which is the smaller and faster version of the memory. And it consists of the registers, the cache, L1, L2 cache, the shared memory, uh, and this part of the memory is smaller in size, and that is why it is much faster. Now the problem with the KV cache is that the sequences grow linearly, uh, and the memory requirement also grow linearly. So because of that, the memory requirement is really huge because you have to store the intermediate representations of your tokens in the KV cache. So storing it in the SRAM is not possible, right? Because you also want it, you just don't want it to be stored somewhere. You also want it to be fast for access. So it has to be stored in a contiguous location, right? So that is where the problem begins. So we have no other option but to store the KV cache in the high bandwidth or the global memory. So when you have a GPU node, it consists of MIG, like it has multiple GPU instances on a single node. So if you go with a GPU like A100, so a single A100 node will have multiple eight at up to 8 GPUs on top of it, and each of these 8 GPUs will have the high bandwidth memory of up to 80 GB. So this memory, even though it is large, the amount of time that it takes to do any operations in this memory uh, is also large. So this memory is large, but it is also slow. And because the KV cache is also large, it stays in the HBM, which is what brings the slowness. And that is why the problem with the internal and the external fragmentation becomes much more severe. Now, what options do we have? So the researchers had faced this similar problem much before facing it in the CUDA. This internal and external fragmentation problem is also present in the operating systems. And the way that they try to solve this problem is using something called a page table. So when the AI scientist they found the similar problem also present in the KV cache, they tried to adapt the page table solution to the KV cache as well, and that is where the paged attention comes in. So this is what the paged attention looks like. Now they have differentiated or they have decoupled the logical address space and the physical address space. The logical address space is contiguous. It starts from memory location 0 to memory location n. So practically you can store a large amount of tokens in a contiguous manner in this logical space. But the logical space need not be stored physically in the same fashion on the disk either, since we have seen in the external fragmentation that the memory can be scattered around in the system. So we are going to exploit this very fact. So the paged attention breaks down the KV cache into fixed size blocks, which can be stored in the smaller memory gaps anywhere. And we have a central table called the block table that basically stores the pointers to these pages or these memory blocks. And then you have an address translation logic that converts the logical address into the physical address, right? So irrespective of where the tokens exist, when I'm reading the data through the logical memory, I'm always going to read the uh, tokens in the correct sequence. So this is how the page retention is able to get past the internal and the external fragmentation and the memory movement problem that exists in the CUDA based system. So when you have fixed size blocks, you can easily fill up all the blocks to the max capacity, and whenever more tokens comes in, you just have to allocate a new block of memory somewhere else and just store a pointer. So the internal fragmentation may occur only in the last block because only those memory addresses are unused. Otherwise, there will not be any internal fragmentation or external fragmentation in the paged attention system. So this is how the paged attention works, and I hope you like it.